Bismillahirrahmanirrahim. Assalamu alaikum. Dear students, first I will revise theories of acid and bases, and then I will tell you more about factors affecting acidity and basicity. You have gone through on your online lectures that what are these factors. For example, you have seen electronegativity, that from moving from left hand side of p block elements from carbon to halogens, acidity is increasing due to electronegativity amongst these elements. What is Arrhenius theory? It is very simple, that dissociation of protons in water will be an acid, and if any compound which is dissociated in water with hydroxyl ions, it will be base. Bronsted-Lowry, proton donor or proton acceptor, and in according to Lewis, anything which is electron acceptor will be acid and electron donor will be base. Then I have told you about how we measure uh, with the scale of pH. It is discussed in detail in my previous lecture. Now I told you about less than 7 will be acidic in nature, and 7 will be neutral, and more than greater than 7 till 14 will be basic in nature. The most important is electronegativity. When your compound has a polar bond, it will be easier for that compound to be dissociated in water. Electronegativity plays very important role to make compounds polar. CH, for example, will not be polar because electronegativity difference is negligible. But when HCl, the bond is polar and there is electronegativity difference is not negligible, so here it will be acidic in nature as compared to CH. Then what hybridization plays its role, I have told you in detail that sp3 is not acidic, but sp is acidic as S character is more, or it is same 1:1 ratio, sp3 25 is to 75 ratio, and in sp2 33 is to 66% ratio. So going towards outer orbitals, hold of proton is less effective as compared to s orbital. S orbital is near to nucleus, so hold of proton is effective as compared to effect of protons on far away p orbital. And bond strength, this as we go down the periodic table, if we take the example of halogens, hydrogen fluoride is not as strong acid as hydrogen iodide is. Here electronegativity is not playing the main role, here size is playing significant role. As we go down the periodic table, the effect of bond strength become more significant as compared to electronegativity. That is why when we have to compare the acidity of p block elements going from carbon to halogens, electronegativity is considered uh, as much electronegative, more acidity. But Although hydrogen fluoride is more electronegative than iodide, but hydrogen iodide is strongest acid as compared to hydrogen fluoride due to polarizability effect or bond strength. Okay, I hope you might have understood it, because in previous classes I have given you this concept clear. Now, inductive effect. You know that this inductive effect might be electron withdrawing or might be electron donating. Electronegative elements, they have a tendency to attract electrons towards itself. They are electron withdrawing groups. The pull of electron density make them conjugate base of an acid more stable. The HCl. In HCl, when Cl negative is liberated, it means Cl negative can exist as chloride anion because halogen has tendency to accept electron. It has tendency to make uh, negative charge, or negative charge can reside easily on it. But if carbon, it will not love to have negative charge on it. So CH will not be broken as C negative, but HCl will be, CH will not be broken to give C negative, but Cl negative is strong enough to survive alone. So it will take risk of being broken. Now what happens when electron donating groups are present? If anything which is already negative, if Cl negative, if it is we are attaching CH3Cl uh, or CH3O negative. CH3O, it is methanol. CH3O negative. So CH3 has electron donating effect. Methoxide is not uh, electron donating group, pushes the electron density away from themselves, making the conjugate base of an acid less stable and therefore making the acid weaker. And then comes resonance. If you see the inductive effect, if we see there is take example of CH tertiary carbocation and primary carbocation. CH3C positive. CH3 has three contributing structures due to hyperconjugation. It has electron donating effect. C is positive, carbocation is positive, and species or intermediates or compounds having positive or negative charge. They these charge species uh, don't like to be positive or negative. So C positive, one is with methyl group. Methyl group has electron donating effect due to hyperconjugation. If it is secondary carbocation, C positive, two methyls are present, it is stabilized as compared to primary carbocation, because six resonating structures are possible due to two methyl groups. So the positive charge is somewhat diluted or somewhat negative, as two methyl groups or six resonating structures are making positive charge less, and three methyls, they are making 9 resonating structures, so positive charge on carbon is less as compared to primary carbocation. This is the best example of inductive effect. So if there is possibility of carbocation, CH3 positive will be very unstable. It will never, it will, it, it doesn't want to be as CH3 positive, but C positive with CH3 or CH2 positive CH3, it is um, somewhat stable than CH3 positive. Secondary carbocation is more stable than methyl radical or primary carbocation, and tertiary carbocation is stable. It can stabilize itself by having negative yeah, or electron donating effect of 3 methyls. And resonance, you know that any compound which has resonating structures, as many as resonating structures will be stabilized. Then factor is aromaticity. If any compound like aromatic conjugate bases are stable and make for stronger acids. Uh, I hope you know anti-aromatic and non-aromatic systems, but here aromaticity anywhere where aromaticity is retained will be stable. And solvation, I have detailed told you about um, what are spectator anions and sorry, spectator ions, and what is solvation, how cations they are solvated by the solvent. If cation, then negative terminal of the solvent will cage them, will solvate them. They will not be naked to be combined again with the proton. Negative terminal will cage or will solvate positive cation, and positive terminal will cage or solvate negative anion. So conjugated bases that can be well solvated by the solvent molecules give stronger acids. But if the compounds are heavy or bulkier due to steric effects, it is difficult to solvate, and due to steric effects they will become less acidic, because we have to see many factors. Sometimes uh, one factor is dominant, at the same time many factors could be seen, should be seen, and they play important role uh, making more acidic or more basic. Okay, now we will see that unsaturated or if unsaturated group is present, how they assist acidity or basicity. This is any acid, carbon acid, proton is removed, then uh, unsaturated group in blue is present, and negative charge after the removal of proton, it is conjugate base. So unsaturated groups, there are many possibilities of unsaturated group. It could be amide, it could be in the form of esters, it could be not only ester, could be acid if R prime is H. It could be nitrile, carbonyl compounds, both ketone or aldehyde or nitro, and pKa values are given. You can compare that which one is more acidic. As you are going towards nitro group, you are seeing that acidity is enhanced, whereas amide ester, carboxylic, nitrile, carbonyl groups, they have almost same pKa, not very drastic change. The reason is that the alpha hydrogens are acidic because the conjugate base is stabilized due to conjugation with the unsaturated group. When proton is removed, negative charge comes, and this amide or carboxylic acid or ester or nitrile or ketone aldehyde or nitro, they they are conjugating, they are stabilizing the conjugate base. Nitro group is very effective to attract. Nitro group is electron withdrawing group. This electron withdrawing or unsaturated group, it is attracting negative charge towards itself. Negative charge is not residing on conjugate base, that is carbon. Now, uh, resonance or delocalization. In my next lecture, I will give you definitions of how you differentiate between resonance or delocalization. So, in your previous classes, you have read about what is resonance, what is the difference, and how delocalization. I have told you that simple example of carboxylic acid. After the removal of proton, conjugate base, acetate anion, it has two oxygens. Uh, so negative charge resides between two oxygens. It is not on one oxygen only. There are two oxygens and negative charge is not localized on one oxygen. It is delocalized between two oxygen atoms. And you show dotted line and inside negative charge. This dotted line means delocalization. And you are making two resonating structures. You put double-headed arrow between one's negative charge on one oxygen and next time negative charge on another oxygen. Two resonating structures, and you uh, show three lines equivalent, or this is the best explanation by dotted line negative charge between two oxygens. So this is actually delocalization, and you have made resonating structures of acetate anion. So you have learned from basic structure organic chemistry that resonance can greatly stabilize charged species because the acidity of organic compound is influenced by the stability of charged species. Resonance plays an important role in determining the acidity of various compounds. Similarly, as inductive factors, there are functional groups that are electron withdrawing and electron donating through resonance. Like I have told you about carbocation, that tertiary carbocation, due to many resonating structures, it has electron donating effect, and it is resonance, no bond resonance, hyperconjugation. And through resonance, electron withdrawing groups increases the acidity. Electron withdrawing groups increase the acidity of a compound, and electron donating group decrease the acidity. Methyl group, if anything, is as for example acetic acid, CH3COO negative conjugate base. If three hydrogens are replaced with electronegative CF3. CF3COO negative is if it is CF3COOH, CH3COOH. You have to compare CH3COOH and CF3COOH. CF3COOH is stronger acid than acetic acid, because acetate hydrogen is doing the thing, but three fluoro groups, they are electron withdrawing. The negative charge will be due to electron withdrawing effect of fluoro groups. Negative charge is no more on oxygen. It is attracted by negative charge is electrons are pulled by three fluoro groups. So oxygen will be oxygen has itself tendency to attract electrons. It will not be uncomfortable to have negative charge on it, and there are two oxygens which are mutually sharing that negative charge due to delocalization, plus three fluoro groups, they are also attracting electrons. So as compared to acetate anion, trifluoroacetate anion is very stable. Now this is simple. I have told you about resonance in carboxylic acid. This is once negative charge on this oxygen downwards, and another time negative charge on this upper, 50% times on this oxygen and 50% times on upper one. And these three lines, these are uh, telling that this is easy to represent these two canonical forms or resonating forms this way, that negative charge is delocalized. It is not localized on one oxygen, twice on second oxygen. No, this is actually hybrid. Both oxygens are having negative charge 50-50% time. So resonance stabilizes the this carboxylate anion. In benzene ring, if we see what happens, this is uh, acid, aliphatic acid, and this is aromatic acid. This is acetic acid, this is benzoic acid. In acetic acid 4.74, and aromatic, I told you that due to aromaticity, the negative charge on after removal, the conjugate base, benzoate, conjugate base, acetate, this methyl has electron donating effect, but this benzene aromatic, it has electron withdrawing. This by electron withdrawing, that negative charge will be delocalized not only between these two oxygens but in aromatic ring as well. So you are observing 4.2 pKa, and vice versa. If we see basicity, what happens, that as much as this negative charge is easily available for proton to be bonded, will be more basic. So this negative charge on oxygen is easily available because it is between two oxygens, but here this negative charge is not only delocalized between two oxygens but also in aromatic system. It is not as easily available as in acetate anion, because there only twice it is delocalized, but due to benzene ring it is uh, further delocalized in aromatic system. Two or three carbons are also involved in delocalization. Five centers are involved in delocalization, so it is much involved in delocalization, but in acetate anion only twice involved, so easily available in acetate anion, so it is more basic as compared to benzoate benz, uh, benzoate anion. Then due to resonance, in a, this is methanol and this is phenol. Methanol, you see functional groups are same, aromatic system and aliphatic system. Aliphatic system 15.5 and aromatic system 10, because negative charge After removal of proton, if you see what happens, that negative charge is an oxygen, negative charge is an oxygen, proton is removed. Methyl is electron donating effect. This methoxide is not as stable as phenoxide. Methyl has electron donating, oxygen is already negative after the removal of proton. So it is destabilizing. Methyl is destabilizing methoxide. But aromatic system is taking negative charge towards itself. So negative charge is not fully present on oxygen. So it is not uh, this system is stable as negative charge is not present only on oxygen, but other three carbons are also involved. They are sharing negative charge, but methyl is neither sharing, but it is giving electron. It has electron donating effect, and it will be vice versa. If phenoxide is acidic, it means it is less basic, and if methoxide is less acidic, it will be more basic. So uh, now if we see, uh, this is branched acid, this is simple linear acetic acid, propanoic acid, ethanoic acid, and formic acid. In formic acid, hydrogen is present. It has neither electron donating nor withdrawing group, but in methyl it has electron donating effect. As chain is increased, more electron donating effect, more branched, more electron donating effect you are seeing. Hydrogen is has no electron donating or withdrawing, so it is 3.75. Easy to proton will be removed easily. Negative charge will be delocalized between two oxygens here, between two oxygens, in propanoic acid between two oxygens, and in this uh, branched acid acetic branched carboxylic acid, negative charge is delocalized between two oxygen. But the difference, that hydrogen is neither electron donating nor withdrawing, but as electron donating groups are increased, acidity is decreased, because after removal of proton, acid carboxylate anion is not stable. So vice versa will be conjugate bases. And then this is these are alcohols. You see linear 1 methyl, not as prominent effect. Branched, this is increased ethyl group, isopropanol, and then branched. You are seeing that due to electron donating effect, the anion or conjugate base will be not stable, and reverse effect of conjugate bases. Then we see some closed rings. It has pK 61, 39, 16, and you see that this is cyclopropene, cyclopentadiene is aromatic in nature, and after the removal of proton, why it is 16? Because it will feel comfortable to remove proton, because after removing proton it will become aromatic in nature. Cyclopentadiene is aromatic in nature, rest these two are not aromatic in nature. So this is the reason that to then I am giving again example: fluoro, acetic acid, chloro, bromo, and acetic acid. Acetic acid is not as much strong as bromo, and then bromo is not as much as acidic as chloroacetic acid is, and the more acidic is fluoro acetic acid. The same, there is an electronegativity due to electronegativity, and in here we see basicity. Ammonia is more basic than tertiary ammonia, and ammonia is less basic than methyl or dimethyl ammonia. Here is a factor that as much as base how basic it has tendency to donate lone pair. Ammonia is donating lone pair, but it is not as basic as uh, primary amine or secondary amine. Primary amine has one methyl group. It has electron donating negative charge is more density of electrons, so more basic. Dimethyl double, this electron donating effect is doubled due to two methyls. It is more basic than primary amine than ammonia, but in tertiary amine, due to bulkier or steric effects, lone pair is not available now. Three methyls are giving electron, they have electron donating effects, thrice they are giving electrons, but now this lone pair is not available because three bulkier methyl groups are hiding, or they are obstacle, they are masking, they are protecting incoming group. It will be difficult for incoming group to attack, or these lone pairs cannot attack due to these bulkier groups any incoming proton, or attack any proton or positive species. Now if we see that in here uh, chloro group is closer to, after the, we have to see after removal of proton, this chloro is near to negative charge on this conjugate base. H will be removed, red part will be removed, so this chloro is near to anion. Here it is far away, it is more far away, and there is no chloro group. So chloro group is, if it is near, its effect is prominent. Due to prominent effect of electron withdrawing group, this conjugate base is stable, and it is stable, so it will easily remove proton. And this is the negative or reverse effect of basicity. If acid is strong, its conjugate base will be weak, and this is the case. Here I have told you about, in ammonia, I have told you about basicity. Basicity of ammonia is less than primary amine and tertiary amine. But sorry, is less basic than primary amine and secondary amine. But in tertiary amine, uh, basicity is decreased due to steric effects. Due to bulkier methyl groups, the lone pair is not in plane, it is distorted, and it cannot, due to distortion, due to steric effects, it could not attack, these lone pairs could not attack proton or positive species. So this is the reason that uh, this tertiary amine should be on the extreme left side, but this is not the case. The more basic is secondary amine, then less basic will be secondary amine, the least basic will be tertiary amine, and ammonia is the least basic of all these bases. Number one basic is secondary, then primary, then tertiary, and then ammonia. I hope this lecture will be beneficial to you. Inshallah Ta'ala, study well and you will understand easily. Assalamu alaikum wa rahmatullahi wa barakatuh.